Okay, recording started, and once again, I see a raised hand. If you want to say something, feel free to step in whenever you want. Okay, and now. So let me open an R console. You know that when I am in the room, I cannot open R Studio. So if you have R Studio, use it. I suggest. Let me open an R console. Here we are. Let me just increase the font. Let's put it at 18. Okay, clear the screen. Okay, good. First, we need to upload the data. So let's start with the file of rainfall evapotranspiration. Evapotranspiration will not be used, but let's start with it. Let me have a look at the file, okay? Because I put the file on the screen. Let me see if my screen is still shared. No. Okay, now the screen is shared. Let me put the file over the screen. Here it is. So there is one line to skip, the heading. Now here you see on the screen two lines, but it's actually only one. In any case, we try by skipping only one, and if we made a mistake, R will tell us. So we have to skip one line, and then we will get, after the scanning into R, we will get, of course, both the data, rainfall and evapotranspiration. So after scanning this file, we will need to remove the evapotranspiration data. So let me go to the R console, which is here, okay? So let's write precip. So I'm not referring to the suggested R code for now, okay? Just because I prefer to write the instruction myself, because in this way I am slower. If I make cut and paste, I am faster, okay? So I prefer to write myself the instructions. On the other hand, keep in mind that, of course, the resulting instruction is different from what is reported in the suggested R code. So no problem at all, just to let you know. Okay, precip scan. So name of the file, I think it is something like, let's see, rain, or I don't remember, rain. Okay, this is the name of the file, which I found by using the tab. Okay, I put the first letter R, and then we put the first letter and then tab. Okay, now let me put a skip equal 1, because it means skip one line. And you see that it uploaded precisely 7,520 data. It's the number that I am expecting, because these are hourly data for 1 year. So hourly, 24-hour a day, plus multiplied by number of days, multiplied by 2, because we have 2 columns of data. You see that it uploaded everything. Okay. Note, I made the check that the number of the data that I scanned is what I am expecting. So this check allows you to avoid mistakes, okay? Now, the problem is that if you read this vector which I uploaded, and let me read like the first 10 numbers, what you see in the vector is an alternation between one rainfall data and one evapotranspiration data. One rainfall data. Why? Because I go now to the file. If you see the file here, the data is are uploaded in sequence. So it's one rainfall, one evapotranspiration, one rainfall, one evapotranspiration. Okay. So in order to remove the evapotranspiration, I have to transform precip into an array. So precip is equal to array. Input data is precip itself. The dimension is 28760. Yeah, I forgot to close around parentheses. And now we are done. when I do this, so when I transform a vector into a matrix, I never remember whether the dimension of the matrix should be 2, 8760 or 8760, 2. So I need to check, okay? Do you understand what I mean? I transform the vector into a matrix. I don't understand whether I obtain the right matrix or the transpose of it. So let me check, because ideally I want that if I make first column and then second dimension from 1 to 10, just to limit it, in the first column I want only rainfall data. Perfect. You see, in the first column I have only rainfall data. If I make the same check second column, I have only evapotranspiration data. Perfect. Now I can keep only the first column. So I remove precip is equal to precip 1, comma. With this instruction, I kept only the first column. Now, if you look at the dimension of precip, it's a vector, not a matrix. Length precip. You see, it's a vector. And it's fine. Now, if I make precip 110, good. These are rainfall data. I can also plot it. Oops, sorry. Control L. Plot precip type equal line. And you see, these are the precipitation data. Fine. The plot allows me to make a check. It is fine. Everything is clear so far? Good. And now I have to upload the runoff data, river discharge. So let me go back here and I clear the screen. So river is equal to scan. I don't remember the file name. Let's see if it starts. No, this is rain. So maybe it's D. No, let me see. Discharge synth. So discharge. Have you seen that if I put only the comma and I press tab, I get a list of all the files in the documenti section, in the documenti directory, in the documents. So I can see that the name of the file I'm looking for is this one, discharge synth. Okay, now I can type this and then tab, discharge synth. Skip equal 1. I need to skip the first line. So I got my 8760 data. Perfect. Let's plot it. Plot river. Just to make another check. Okay, and that's it. Perfect. This is clearly, it's a good representation of an hydrograph. Okay, these are synthetic data. So, I mean, synthetic data means that they are not observed, they are produced by me. On the other hand, if we assume that they are observed, first of all, it's realistic. I mean, it is a bit strange. I would say this is strange because when you look for, when you plot discharge data from a river, what are you expecting? You are expecting to see in our climate, I mean, this is 1 year. I'm expecting to see high flows in spring and fall season and low flow into summer. If it is, if I knew that it's an Italian river. If I knew that it's an Italian river, I also know that it may be that I have a different regime in the Alps where I get low flows in winter, low flows in the fall season, and high flows in summer because they are dominated by snow melt, ice melting. Okay, so in a way, these are the two types of river flow that I would expect. This one is a bit strange because apparently there is no high flow season. It's regular along the year, and I would say that it's a bit strange. But anyway, let's. It is. They are synthetic data, so it's not strange. And another thing, if it was observed, I mean, at peak flow in 1 year of 100 cubic meters per second, it's quite a significant river. It's not the Po River, but I mean, 100 cubic meters per second in 1 year, which means that if I had like 10 years, the peak would be higher than that, and probably higher. This means that 100 cubic meters per second is something, I mean, significant. It's smaller than, for instance, the Reno River at Bologna, because the Reno River at Bologna, usually you get a peak flow in 1 year that is usually it's around 500, something like that. But still, it's a significant river. Okay, good. Now we have to apply our linear reservoir. Oops, sorry. Okay, at this stage, I think it's better if we go and look for our R code, because otherwise we lose any reference with it, and I don't think it's a good idea. So suggested R code is here. Okay, so first, this is a code that makes only one run of the linear reservoir. Let's try to study it, okay? And let's, first of all, let's remark that we have different values of the variable. You see here, river, what I called river is called river flow. So we have to take it into account. And what I called precip or something like that is called rainfall. Okay. And we have to take this into account. Let me change the name of the variable. Okay. So river flow is equal to river, and rainfall is equal to, I think it was called precip. Let me see, I don't remember. Precip, yeah, precip, perfect. Now we are done. And we can remove river and precip. Okay, everything is clear so far? Good. Questions? No questions. Okay, this makes only one run. So let's first of all define the vector of the simulated river flows. Okay, this is not necessary, but I prefer to define it soon. Why I want to define it soon? Because if you use the vector into a force cycle, and I need a force cycle because I need to run the linear reservoir for 1 year. So I need to run it every hour for 1 year. Then into a force cycle, you can't define a vector. You have to define it earlier. Okay. So let me define this. So I copy in this case, but you see it's a replicate of zeros. Zeros for a number that is equivalent to the number of hours in a year. So here it is. Okay, now let's define a trial value for k. And k, remember, is in a way, we have to define it in seconds. And I said that k, which is the only parameter of the linear reservoir, is comparable to the time of concentration. Okay, so here I assume that the number of seconds in 1 hour is 3,600. I assuming that k is equal to 300 hours in seconds. 300 hours means more than 10 days. It's a bit long. So because a time of concentration of 10 days for a river with a peak flow of 100, it's a bit long. But this is a trial value, so no problem. I just want to make you aware of the reasoning that an expert should make. Like K should be time of concentration in hour. A river of 100 cubic meters per second as peak flow. What could be the time of concentration? I would say less than 10 hours. In this case, we assume that K is 300 hours. One thing, keep in mind that what I'm doing now is an attempt to assign to a model parameter a physical value. Okay, so by equating K to the time of concentration, in a way, what I'm doing is to look at the physics, the physiographic of the catchment, and relate a parameter of a mathematical model to a physical behavior of a catchment. Okay, this is something that we should always do, because in a way we have to make our models in a way matching the reality. Okay, so it is something that we always have to do in order to understand better what the model does. On the other hand, we know very well that there is uncertainty in any modeling process, and uncertainty needs to be compensated by model parameters. So if the model parameter assumes a value that is unrealistic from a physical point of view, this is something that may happen. And it's not necessarily indicating a failure. Okay. As far as you are aware, like, this K value is not really realistic according to theory, but it works. This is fine. Okay. As long as you make this reasoning. So you notice that it's unrealistic, but you accept a compromise to make the model working, to compensate for the approximations. I hope that the reasoning is clear. Okay, so let's use this K value and see what happens, I mean. Good. Okay, now this is input data. This is the area of the basin, of the catchment, in meters, in square meters. So we said that it's 1214 square kilometers. If you want to transform it in square meters, you have to add 6 zeros, okay? And then the time step, 3600 seconds. And then you need to specify the time step of the model. It's sorry, it's 3600, and then you have to specify the number of time steps you want to simulate. It's 1 year, so it's 8700 plus 60. And then let's put as initial value of the storage into the reservoir W0. Okay, let's copy it. Good. Now we are ready to apply the linear reservoir. We defined everything: area of the catchment, the time step, 1 hour, the number of time steps we want to simulate, 8700 plus 60, and the initial value of the storage in the bucket in the linear reservoir, 0. Okay, good. Now, look at the computational cycle. It is very simple, okay? And this is the way you understand how it works. It's a numerical approximation. Actually, it's not involving the computation of the integral. We don't look at the computation of the integral here. And so we don't use any summation. What we do is very simple. What we do is, let me make a sketch over the blackboard. 1 second, because I want to change the camera. And let's see. Okay, perfect. Let me put the camera here. And let me pin it. Okay. Let me have a look at the cycle. Before I go to the blackboard, I need to get it clear how it works. Just 1 second. Okay, yeah. So what we do is, as I said, very simple. We get our bucket. We get our bucket where we get rainfall in. And then we have Q out, and then there is W here, okay? Okay, good. So what we do is start, and we started the time first hour. What happens in the first hour? I start, first of all, the first hour with the W equal to 0, okay, or better, W0 equal to 0. This is my start at the first hour. And then what I get at the first hour, I get rainfall in. Maybe it's not given for sure, but let's suppose that I get some rainfall in. So in the first hour, the first thing that I do is compute W1 is equal to W0 plus P1. So rainfall increases the volume contained in the linear reservoir. So I take W0 plus P1. Of course, this is P1 times, we should write here, times delta T, which is the time step, because P1 is intensity of precipitation. And so intensity should be multiplied in order to get the volume, the intensity of precipitation multiplied by the catchment area. So it is a volume over time. If I want to add it to a volume, I have to multiply by the time step. And then I get the storage at the end of the first hour, W1, okay? And then I can compute Q1, which is W1 divided by K. And then here I note something that if your eyes are careful, you note something that it looks a bit odd, because what I'm doing, I am taking volume into the reservoir at the end of the first hour by assuming that precipitation, all the precipitation is accumulated. Actually, during the first hour, some flows already goes out. So it's not fully correct what I'm computing here. It's an approximation, you understand? Because here I am assuming, in making this first computation, W1, I am assuming that I have no flow. So it's an approximation, you understand that? And then I compute the flow by assuming that all the precipitation was accumulated. So it's an approximation, of course. And then, given that I computed the flow, I have to subtract to the previously calculated volume, W1, I have to subtract the flow that went out. So I have to make another computation of W1. So W1 is equal to W1 minus Q1 delta T. In doing that, it may happen that I get a W1 value that is lower than 0. It may happen because in the computation, in doing the computation in this way, I am overestimating Q1. It is overestimated. You understand why? If you follow these three equations, here I compute W1 by assuming that there is no outflow. Everything is accumulated. So I am overestimating W1. So in the second step, given that W1 is overestimated, I am overestimating Q1. And then when I compute the new value of W1, if Q1 is overestimated, I could get a value that is lower than 0. So I have to put here a condition. The condition is W1 equal to 0 if W1 is lower than 0. So let's see what's written here. Look at the code. Now let's try to make the selection and see if the screen remains there. Yeah, this is the mystery of informatics, you know. So W is equal to W plus rainfall I, because this is a computational cycle. So at the first round, I is equal to 1. Divided by 1,000. Why divided by 1,000? For unit conversion, rainfall is in millimeters per hour. So I have to divide by 1,000, okay? And then divided by time step. Why? Because rainfall is hourly rainfall. So given that I want the time step, the time is expressed in second here, hourly rainfall needs to be transformed into rainfall per second. So I have to divide rainfall by time step. And then I multiply again by time step. Why? Because it's here. Rainfall, if I want to get the accumulation of rainfall in the time step, I have to multiply it by delta t. And this is the reason why here you get the multiplication by time step. Of course, you may say, okay, you could simplify this. We don't need to divide by time step and multiply by time step. Okay, it's written for the sake of clarity. Okay, good. And then here there is the computation of the river flow. Okay, and then here the new computation of the volume. Volume is equal to volume minus river flow times time step, like it's written here. And then here there is the condition: if W is lower than 0, W is equal to 0. That's it. And I computed river flow for the first time step, like here. Now I repeat in the fourth cycle, and I get river flow at any time step. Be careful, I didn't introduce the conversion, I didn't take into account the area of the catchment, so it is done here. After the end of the fourth cycle, river flow is simulated, is multiplied by the area of the catchment. And then here there is a plot. The plot is river flow simulated, and it's for comparison, it is plotted the observed river flow. So we are ready to start. Cut and paste. Copy. Of course, the simulation that I obtain is for the given value of k. Okay, let's see what happens. Let's clear the screen, paste, and that's it. Let's see the graph. And this is the graph. I think in red is the observed, and in black is the simulated. Okay, this is the first trial. So let's have a look at this graph. What do you see in the graph? First, you never have to expect a perfect simulation. If you get a perfect simulation of an observed time series, perfect, it means that you made a mistake. Okay, and you know, when I was a PhD student, I aimed to get a perfect model. This was my dream. No, like, okay, I will find the solution. So, and the perfect model. And once I made a mistake, and I uploaded I plotted twice the observed data instead of observed versus simulated, and I was super happy. Yeah, I made it. It's perfect. And so, first advice that I give to you: a model is never perfect. Okay, if you get a perfect model, don't say like I did. Yeah, I made it. And of course, I realized after about a couple of minutes the mistake, because so I mean, if you see a mismatch, that's fine. On the other hand, we said that by looking at the mismatch, we need to wonder whether it's possible to improve. And by looking at this one, I would say, yeah, we need to improve because it's really poor. And what is poor here? First of all, you see that the peaks are overestimated, or I would say some of the peaks are overestimated, but what is clear here is that the shape of the hydrograph is not good, because it looks like the hydrograph is fatter. Okay, so it's the red one is more peaky, and what is making the hydrograph fatter? It's storage. So if you get a catchment with a very low storage capacity, the hydrograph is more or less peaky as the yetograph, as the graph of rainfall. If you get catchment with a lot of storage, the hydrograph with respect to rainfall becomes fatter. So storage makes the hydrograph fatter. Of course, given that volume is conserved, but actually here I didn't multiply for 0.5, and this is why I think there is something wrong here. I forgot to multiply by 0.5. Let me just, okay, but let me finish. Storage makes the hydrograph fatter. What is making storage? It's K. You see? And we said this already a couple of weeks ago. We said if you increase K, you increase the storage. So W gets larger. So by looking at this hydrograph here, I would say I have to decrease K because I need to make the hydrograph thinner. On the other hand, if you make the hydrograph thinner, the peaks goes up. So I was a bit concerned because I said, okay, now I decrease K, I make the hydrograph thinner, but the peaks will go up. So it's a problem because the peaks are already overestimated. But actually, I then realized that I forgot to multiply by 0.5. At least let me see if I indeed forgot. Let's see. Yeah, here it's rainfall that is multiplied. So for sure, I am overestimating the volume. So I mean, let's change this, okay? In order to change this, I need to copy it over a notepad. And if I want to make the change, otherwise it becomes too system. Okay, let me see. Sorry. I have to look in accessories. You have to be patient. When I work with Windows, I am slower. Okay, so let's say rainfall E times 0.5. Okay, it's very simple. I just have to change this. Okay, and now let's see how the graph changes. Copy and go to the R console and paste. Okay, let's see. Okay, perfect. Now you see that the black hydrograph is fatter and the peaks are underestimated. Okay, this is perfect. I need to change K to make K smaller. Good. Now let's see. Notepad again. And let's make K here. K is equal to, earlier it was 300 times 3600. Now let's put 150 here, okay? And let's make it again. Much better, much better. But still, it's still a bit fatter, and the peaks are almost all of them underestimated. So let's try to make K a bit smaller, okay? I clear the notepad. Let's try K100. So it's 100 hours. It's still a lot. It's still a lot for a catchment of this size, but it's okay. Okay, now it's even too good, you know. It's unrealistic. It's almost perfect. It's unrealistic. So we are close to the optimum here. And I think probably the optimum will be something like, first of all, you see at the beginning, there is our assumption that W is equal to 0. That is not reproducing well the start of the hydrograph, but the initial condition is vanishing its effect very soon. So if we now, you see that still the peak is a bit overestimated and the hydrograph is a little bit fatter. So if we now go with 80, I think that we get to perfection, which is not a good thing. 80 here. You see, it's perfect. So, but I think this example is instructive because it allows you to reach the perfection. It's not yet perfect, but it's almost perfect. But it's not realistic. As I said, if you get a result like this in a real world application, you should get very suspicious because it can't be like that. Okay. Good. So I have to correct my suggested R code because I forgot the 0.5 there. I will change it soon. On the other end, we still have to make the automatic optimization. But now you have the means for doing that because we tried with the linear trend estimation, you learned how to use the optimize function. What you just need is to write a function computing the linear reservoir, which is easy. Anyway, you can try it, but I think next Monday we can take 10 minutes in order to do it together. And for today, I think we can stop here. Any question? Let me check if there are questions in the chat. Okay. Okay, good. Thank you very much. And for the student who asked about exam subscription for Science of Climate, I will make a check, but I think that you have to refer to this your student secretary. So please, anyway, check with them. I am making a check myself, but I think you should refer to them. If you have any problem, let me know. Okay, thanks, and let's stop the registration.